Hello. So yeah, hi everyone. Today I wanted to go through one of a thesis that one of my professors suggested. So it's the thesis is titled "Modeling Performance and Power for Energy Efficient GPU Computing General Purpose GPU Computing." It's the thesis is by Sunyo Hong, if I'm pronouncing it correctly, and it was published in December 2012 from Georgia Tech. And their supervisor were Dr. Hyosun Kim. And yeah, so let's start with it. So I'll skip the acknowledgement part. We'll start with uh, we'll start with the first chapter. Let's see. So yeah, Chapter 1 Introduction. Numerous problems that require high computing power have existed since the emergence of first computers. Okay. However, although computing power has consistently improved from increasing clock frequency, that improvement has mainly focused on the performance of single threaded application. As a result, complex problems still fell into the hands of people working in supercomputing centers. So yeah, if you know, like if I'm correct, initially like when the computation load started increasing maybe in the 1980s or 90s, people the companies who were manufacturing CPUs, they were they were trying to increase the clock frequency to get maximum compute out of it, right? So that went till a point, I think it was 2000, early 2000s, and then they started increasing the cores instead of just working on one core and increasing the frequency. So I think yeah, that's what they're talking about. uh, Given the particular time frame in which we are living, this is no longer case, which is true. And also, like, this is from 2012. Okay, so yeah, like, we have to keep that in context. The thesis is from 2012, and a lot has happened since then. But yeah, this was the early period of when the GPU usage was picking up. So I think yeah, the CUDA came out in 2008, or 7 or 8, I think so, and this is from 2012. So yeah, this is still pretty much early. Given the particular time frame in which we are living, this is no longer the case. With the advent of graphics processing unit, ordinary programmers who used to have access. Okay, let me keep my mic a bit down or far so that the noise is not. Okay, so yeah, I think this is good. Given the particular time frame in which we are living, this is no longer the case. With the advent of GPU, ordinary programmers who used to have access to only multi-core processors now have access to hundreds of execution units. So they are talking about the CUDA cores and the threads inside them. So additionally, with emergence of general purpose GPU computing, so that is GPGPU, the outcome is spectacular. A high number of programmers across the globe started to convert their scientific and engineering application to GPGPU computing. Many have reported speed up by a factor of more than 100. So I think this number would be way more now, in multiples of this. But yeah, as I said, this is pretty much early in the development of CUDA, GPU usage, all of that. So yeah, 100 is still great. On real world applications, it appears on the surface as though computer development has reached the ultimate goal. However, it is important to assess whether this in reality has actually occurred. The design of GPU architecture has advanced at a fast rate in the market. Even a heterogeneous processor which exhibits both CPU and GPU characteristics began to emerge in the market. Okay. However, such a change is not fast enough for a programming model and programmers. Most programmers are still likely to keep optimizing their application performance blindly. That is, they keep optimizing the programs without first understanding the essential features of the architecture. I think this is still true, because a lot of developers that even I personally, right, like we write the code as software developers, but we don't really care too much about how the hardware behaves, like what's the architecture, how the code that I have written behaves in a certain way with the hardware, and also how can I optimize my code so that it uses the hardware efficiently. I think that's still the problem. There is a gap between hardware and software. So yeah, I'll read that. So most programmers are still likely to keep optimizing their application performance blindly. That is, they keep optimizing the programs without first understanding the essential features of the architecture. This is a serious problem, and it may eventually lead to a higher cost for software development in terms of time and money. Okay. Furthermore, although profiling tools exist in addition to other parallelizing tools, they do have one limitation in common. They neither provide insightful knowledge of the architecture nor capture essential architectural features that affect performance. Thus, the relevant question, we have a lot of tools now, but yeah, let's read forward, let's read ahead and see what exactly they're talking about. So, thus the relevant question that becomes, rather than merely running the tools as simulation, is it possible to use only essential features and gain insight into the performance? Thus the relevant question then becomes, rather than merely running the tools or simulations, okay, is it possible to use only essential features and gain insight in the performance? Other than running the tools or simulation, it is possible to use essential. Okay. So, is it possible to dig deep into the performance of the software? That's what they're talking about. Using only the essential features. So, to this question, we propose an analytical model that predicts performance for GPUs in 2009. Okay. Analytical model that predicts performance for GPUs in 2009. The model is based on a technical premise that memory access cycles between multiple warps can be overlapped. The model is based on a technical premise that memory access cycles, right, between multiple warps can be. So warps are, if I'm not wrong, I just have a basic knowledge, but yeah, warps are groups of threads that execute a kernel one instance in a given instance, right? So I think so that's warps. So the model is based on a technical premise that memory access cycles, so you go fetch something from the memory and come back between multiple warps. So they're talking about different warps, so different groups of threads can be overlapped. The model is based on a technical premise that memory access cycle between, okay, and that amount of memory level warp parallelism, MWP, amount of memory level warp parallelism, okay, depends on, so basically multiple warps, right, multiple groups of threads are trying to access memory all at once. So that's what they mean by memory level warp parallelism, right? Depends on available bandwidth and internal dynamic random access memory, DRAM cycles. Okay, yeah, it depends on the RAM of the device as well, right? How much memory or can be fetched by groups of threads in parallel, right? So let's say there are multiple warps, multiple groups of, let's say, 32 threads, right? They're trying to access the same memory or maybe even different memory or locations. That would depend. The higher the amount of RAM, the more easier it is, right? So that's what they're trying to say, that amount of memory level warp parallelism, right? So groups of threads, that's called warp, in parallel they're trying to access memory, right? That depends on the bandwidth and internal DRAM, right, dynamic random access memory. Thus, by precisely knowing the effect of bandwidth and types of memory accesses, an effective memory latency can be calculated, thereby predicting the application's performance. Thus, by precisely knowing the effect of bandwidth and type of memory accesses, an effective memory latency can be calculated, thereby predicting an application's performance. Precisely knowing the effect of bandwidth, type of memory accesses, you know the bandwidth of the amount of memory that can be transferred if you know that, and the type of accesses that is happening, right? An effective memory latency can be calculated, thereby predicting an application performance. Okay, that makes sense. The benefit of this modeling approach is that, unlike other established profiling tools or hardware performance counters, profiling tools, okay, the analytical model only uses key features of the GPU architecture to predict performance. So basically, you don't need input from the hardware. Like basically, hardware has performance counters, right? So I think there are special registers on the hardware that have performance metrics of the hardware. So other profiling tools or hardware performance counters that already exist, the benefit of their model is that you don't need that. You only need key features of the GPU architecture. I think so. Let's say the bandwidth, the types of memory, those are already constant. So if I give you an architecture, a type of an architecture, I think you can basically, it will remain constant throughout the life of that GPU, right? So this is, whereas these things, the performance counter values, they change dynamically, right, as the usage goes on. So that's their benefit, the benefit of the model that the author is proposing, or they have proposed and published. So the model is based on a technical premise that, the benefit of this modeling approach is that, unlike other established profiling tools or hardware performance counters, the analytical model only uses key features of the GPU architecture to predict performance. This means that a person using this model is able to visualize performance determining factors in a graph. This means that a person using this model is able to visualize performance determining factors in a graph and point out the factors that limit the performance. Okay. Performance. A person using this model, this means that a person using this model is able to visualize performance determining factors in a graph and point out the factors that limit performance. Okay. Therefore, a programmer not only finds performance limiting factors, so basically they are saying that their tool, their model can help you find the bottleneck or like what's that limiting factor that's limiting the performance of the GPU or the software that they are trying to run, like what's the limiting factor there in terms of the hardware. So that is what their model can help visualize that. This work also provides several techniques for performance optimization by suggesting the generation of more threads. This work also provides several techniques for performance optimization by suggesting generation of more threads, notifying that memory bandwidth is insufficient, and improving a memory transaction type to coalesced memory access. Okay. I think these things will become more clear as we go ahead and read. Go ahead with the other chapters and really go into the depth of these models or techniques. So another important aspect of GPU kernel optimization is power and energy savings. So this is something that I am interested in. So another important aspect of GPU kernel optimization is power and energy savings. More programmers so far have focused on performance optimizations because traditionally optimizing for performance is better for energy savings, since the execution time reduction often outweighs the benefits of other energy saving techniques. So think about it logically, right? So if you have a piece of code, if you optimize it for time, right, so you make it more time efficient, then that would reduce the execution time, and then at the end it would also lead to energy savings, right? So that is what programmers traditionally used to do, right? So as it says, most programmers so far have focused on performance optimization because traditionally optimizing for performance is better for energy saving, since the execution time reduction often outweighs the benefits of other saving techniques. Okay, so yeah, maybe this was true back then. Now there are more techniques that could be, maybe, arguably more, can lead to more energy savings compared to just the performance optimization. But yeah, however, in the GPU architecture, this is no longer true. In my previous work, it was demonstrated that in some application there are different optimization points for energy savings. This observation, so in some applications, so let's say you have multiple applications, there are different optimization points for energy savings. So yeah, in a given application there are multiple points where you can optimize that application to make it more energy efficient, right? So that is what this work proved, that for any given application there are multiple points which you can optimize to get energy savings. This observation is based on a detailed power model that I developed by using an empirical method and a previous performance model. I proposed the integrated power and performance prediction framework. So this is a framework. Okay, highlight this. To estimate an optimal thread and block configuration. Estimate an optimal thread and block configuration in compute unified. You see, this is CUDA. Yeah, so CUDA is introduced here. I propose the integrated framework to estimate an optimal thread block configuration in compute unified device architecture language. Optimal thread and block configuration. Okay, so yeah, I mean, in the GPU, the architecture is, you have the grid. A grid is divided into multiple blocks, and blocks are divided into multiple threads. So what their work did is, they estimate an optimal thread and block configuration. And I think, yeah, the blocks, inside each block, how many threads are there? There's a maximum threshold of threads, but then you can configure on your own as well. So basically what they do is they estimate an optimal thread and block configuration, like, okay, these are the number of threads and blocks that you should have to get optimal performance for in CUDA language. So in CUDA code, CUDA kernel codes. So in their work, in this work published in ISCA 2010, is based on, inside that, not all GPU cores need to be activated depending on the type of application. Furthermore, this work can be used with other power management techniques such as core gating and voltage scaling. In essence, the work demonstrates the benefit that when power gating technique is employed for a bandwidth limited application, okay, I have to see what this means. Let me just. In essence, the work demonstrates the benefit that when power gating technique is employed for a bandwidth limited application using fewer cores. Okay, so let me open this. Just a second. Let me open a new. So yeah, I'll ask this to ChatGPT or GPT-4 to explain this. Okay, so it says power gating technique, right? So this is an energy saving technique used in electronics and computing. The idea is to turn off the power supply to certain parts of a chip when they are not in use. By doing so, it reduces the energy consumption of the device because inactive components do not consume power. Yeah, I mean, it makes sense. So I mean, think about it, right? So you have multiple cores in the GPU, right? You have two types of application. One is which uses, which has small GPU utilization, so it doesn't need a lot of compute. In that case, do you want to keep all the CUDA cores active, like all the electrical or electronics component of the GPU active? No, right? You don't want that, because that would consume energy, like additional energy that is not even needed, right? Because the compute that the application demands is very less. In the second case, the compute demand is huge, so in that case you want to provide electricity to all those components that are being used, right? So which will ideally be more than the previous case where the compute demand was really low, right? So then basically power gating technique is when you don't need when you don't need to use certain electrical or electronics component, you don't give them electricity, like you stop the electricity supply to them, so it saves energy, right? So basically you're gating the power. That's why it's called power gating technique. So let's read this again. The work demonstrates the benefit that when is employed for a bandwidth limited application, using fewer cores save more energy, more than 10. Yeah, I mean, it makes sense. Yeah. As I said, right? Using less number of cores, using power gating, you turn off the power supply to those cores. It will lead to energy lesser energy consumption, and they say it's like 10%, more than 10%. So yeah, in the future, we envision that a computer system will contain hundreds of cores. Yeah, that's I don't know what's the current scenario, like how many cores do computer system have, but collectively, if you take multiple GPUs, like systems that have multiple GPUs, they for sure will have hundreds of cores. So yeah, I don't know about like what's the maximum that a single GPU has, the number of the amount of cores. Let's ask ChatGPT that. Okay, so GPT-4 says, as my knowledge cutoff is April 2023, the trend in computing has indeed been towards multi-core processors. Some high-performance systems, particularly servers, already feature CPUs with very high number of cores. Okay, I don't want CPUs, but AMD's EPYC server processor has versions with up to 64 cores. Intel's Xeon scalable processor also offers versions with substantial number of cores. So for high-end consumer-grade computing devices, 16, 24 and 32 cores are available. I mean, like, yeah, it's we see quad core devices and all, so hundreds of cores is not like for single device. I don't think it's been achieved yet for CPU at least. Okay. The challenge lies in the fact that some applications run more efficiently on a CPU than a GPU. For this reason, most future processors will be heterogeneous in nature. Yeah, I mean, you need CPU. You cannot be just using GPU, right? There are certain tasks that you need CPU for, so people have CPUs, and then complementing that, you have GPU that's used for graphical tasks, games, training, deep learning models, things like that. So, but yeah, like you need CPU as well. So yeah, that's true. We need heterogeneous systems with both CPUs and GPUs. To address that technique, I co-developed a dynamic compiler system that reduces the programmer's burden of mapping between CPU and GPU based on the performance model. Kilin effectively predicts how much computation needs to be done on the CPU and on GPU. Okay. Moreover, Kilin dynamically recompiles and performs automatic partition of data depending on input and workload characteristics. Performs automatic partition of data depending on okay. The work shows that best performance is achieved when the CPU and GPU are effectively used together. While this dynamic approach finds a balanced workload distribution after a profiling phase, to reduce the overhead of profiling time and to provide insights in the CPU and GPU analytically, I propose a static time approach that requires instruction mixture and input data size information. While this dynamic approach finds a balanced workload distribution between CPU and GPU, so basically for a given task they are trying to predict the load distribution between a CPU and GPU, the work, right? So and then what kind of distribution can lead to the most efficient performance, like how can CPU and GPU be used efficiently together. So while this dynamic approach finds a balanced workload distribution after profiling phase, to reduce the overhead of profiling time and to provide insights into CPU and GPU analytically, we propose a static time approach that requires instruction mixture and input data size information. This work will leverage my previous work, which models performance of GPU architectures. Static time approach that requires instruction mixture and input data size. Finally, this research makes great strides in analytic work domain. My is it thorough, informative, and I can extend it to a compiler domain to guide performance optimization or architecture simulation domains to provide fast and scalable simulation time. Because of this research, researchers and will program their applications for GPGPU computing more efficiently. Okay, let's go to chapter 2. Okay, let's go through this as well. An analytical model that provides performance and power an analytical model that predicts performance and power, provides insights, and can assist energy efficient execution for many core architecture, which is not limited to a GPU. The remainder of this document is presented for. So, chapter 2 and 3 provides research work for modeling GPU performance and power. I think we talked about this. Then chapter 4 presents the thermal analysis using customized thermospacer and thermocouples. I don't think they talked about this, but this should be interesting. She presents the throughput model that is a significant extension of the performance work. This work has modified the analytical model structure from bottom up, which enables a more thorough analysis in terms of bandwidth, achievable performance given instruction mixture, and memory effect. So this is the last thing that we talked about here, I guess. So chapter 6 presents the related work to analytical modeling for performance and power, OpenCL, and energy efficient execution in the heterogeneous system. So this is the CPU and the GPU combination that we talked about, the work distribution, the efficient work distribution to get efficient. Like for any given task you need to use GPU and CPU, combination of them. So how do you efficiently distribute work between them? So I think this is what they're talking about. Chapter 7 presents the conclusion and future research directions. So it would be interesting to go through future research directions and see like what has already been achieved. So let's go through chapter 2, modeling GPU performance. To provide insight into performance bottleneck in massively parallel GPU architectures, an analytical model is proposed. Okay. To propose insight into performance bottlenecks. So let me highlight this so that we know the goal. The model can be used statistically without executing an application. So, given an application, they will give you insights into the performance bottleneck that application can have if you run it on a GPU, right? And because it's a static model, like you don't even need to execute the application itself. So that's always good. Like if you don't have to interfere or given a code, if you can just do statical analysis and give your results on top of that, I think that is always better than executing the code. And it's also lightweight, so it will save energy in itself. The basic intuition of the model is that estimating the cost of memory operation is a key component of estimating the performance of parallel. So the basic intuition of the model is estimating the cost of memory. Okay, so let me do this. So basically what they're doing is they're estimating the cost of memory operation, the memory access operations that we talked about from the DRAM. So I think they touched upon this in the first chapter. So the basic intuition of the model is that estimating the cost of memory operations is the key component of estimating the performance of parallel GPU applications. So they are relating both these points. So if you can estimate the cost of memory operations that are happening for application, you can get the bottlenecks of performance, or you can estimate the performance of GPU applications. Let's say more an application is using memory, like it's the performance is higher than something that's using quite less memory, right? So the execution time of an application is dominated by latency of memory instructions, but the latency of each memory operation can be hidden by executing multiple memory requests concurrently. So the execution time of an application, right? So let's say you're running an application, the time it takes is dominated by latency of memory instructions. So what they're saying is when you run an application, the amount of time it takes, right? A huge chunk of that time is formed by the latency of memory instructions, right? How many memory instructions you need? Are they sequential? Are they in parallel? Like the amount of memory that is being fetched, all of those things, right? So that forms a major chunk of that execution time of that application, right? But what they're saying after that is the latency of each memory operation, right? The time it takes can be hidden by executing multiple memory requests concurrently, right? So instead of, let's say you have to do 10 memory access requests, if you do them sequentially and if you do them all in parallel, like obviously the one that is done in parallel take less time, right? So that's my understanding. Just give me 1 second. I'll be back. So yeah, let's continue. The execution time of an application is dominated by the latency of memory instructions, but the latency of each instruction operation, each memory operation can be hidden by executing multiple memory requests concurrently. We talked about this by using the number of concurrently running warps. So yeah, as I think, yeah, we talked about this already. A warp is a batch of threads that are internally executed together by the hardware, right? The groups of threads is called warp. So yeah, by using the number of concurrently running warps, the amount of memory bandwidth consumption and the memory types, the number of overlapping memory access can be predicted, which is quantified as the memory warp parallelism metric. Let me highlight that. By using the number of concurrently running warps, so let's say there are 4 warps running. So 4, and each warp has, let's say, 32 threads, right? So 4 into 32, right? So that's the number of from that, like you get like 4 into 32 threads. Each thread, let's say, does x number of memory operations. I'm just assuming, right? Like then you can get the amount of memory bandwidth consumption from that, because all of them are running in parallel, right? All the threads in a warp execute a CUDA kernel in parallel, right? So all of these threads access different memory locations, but then they do it all at once, right? So then you can get the bandwidth of let's say, if, as I said, there are 4 warps together, you can get the bandwidth of memory that is being used by those warps. So the amount of memory bandwidth consumption, the memory types, the number of overlapping memory accesses can be predicted, which is quantified as memory warp parallelism metric. So basically, yeah, this last thing, the number of overlapping memory accesses, that is called MWP. That's quantified as MWP, which is memory warp parallelism. Another metric that models computation is defined as computation warp parallelism. Computation. Okay, so basically similar, but for computation. This is for memory. This is for computation. This as well. Okay, let me save this. Just give me a second. Let me just save this. Okay, so it's saved. Let's go. By using the number of concurrently running warps, so yeah, CW represents how much computation can be done by other warps while one warp is waiting for memory values. So how much computation can be done in parallel by multiple warps that are being executed. So in the memory we saw that the MWP, that is memory warp parallelism, is MWP metric is the number of overlapping memory accesses that can be predicted, right? So overlapping memory accesses, that's MWP, overlapping computations that are being done while one warp waits for, let's say a warp wants to access a memory location, but other warps that are running in parallel right now are already trying to access that, right? So the computation at that moment when the parallel execution is happening, that's called CWP. CWP is similar to the arithmetic intensity metric used in the GPGPU community. Okay. Intensity. Number of mathematical operations per memory operation. So this is. Can I change the color? Okay, let me see if I can. Okay, let's keep it. What is this? See, arithmetic intensity metric that is used by the GPGPU community is the number of mathematical operations per memory operation. So for given memory operation, type of operation, basically the number of mathematical operations that are happening. So that's called arithmetic intensity metric. By using both MWP and CWP, the effective cost of memory request can be estimated. Just a second. So yeah, the effective cost of memory request can be estimated by predicting overall execution time of a GPU program. I think yeah, because like from these values you can get the maximum bottleneck, like the maximum memory that is being used and maximum computation that is being done at an instance, right, for any given application. So from that you can predict the execution time, because that's the bottleneck, right, and that would give you the maximum bandwidth of the computation and memory. So depending, like based on that, you can predict the overall memory and computation that will be used by the application, right? So the effective cost of memory request can be estimated. Memory request, effective cost of memory request, thereby predicting an overall execution time of a GPU program. Okay. Background. A brief background of the GPU architecture and the programming model is discussed. Okay, I think this should help us. I have some idea, but then yeah, this should set the base for it. So let's go through this. Background on programming model. The compute unified device architecture. Okay, it sounds so weird. Like CUDA, everyone knows what CUDA. Like okay, the term CUDA, but like I don't know how many people know. It's compute unified device architecture. Its programming model is similar to a single program multiple data. So yeah, there is something called SIMD as well in CUDA, that's single instruction multiple data. So I think yeah, this is because I've heard about SIMD, but yeah, I didn't know there is something SPMD which I think is similar as well. So that's what they're saying. The compute unified, that is CUDA programming model, is similar to single program multiple data software model, right? So I think yeah, what this means ideally, especially like SIMD, is we talked about warps, right? So warp executes at once, right? Let's say one warp is being executed, it has multiple threads. Now all those threads, they run the same kernel code, but then the code is same, the instruction is same, but the data that they access, the data location, the type of data is different, right? So let's say you are doing vector addition, just to give an example, two arrays, two vectors, you are adding them, they're 124 size, right? So then you will have, let's say 124 threads, each thread adding one element at a time, right? So then you can say there are 124 operations in parallel. Then the instruction is same, addition, but then the data that is being fetched is different, right? In first index, zeroth, first, second, third, so all of them are different, right? So you'll have to change the data location as well. So same instruction or single instruction, multiple data. So I think yeah, this is same as that, single program, multiple data, right? So in other words, each thread is, so yeah, let's read this. In other words, each thread in a CUDA program executes the same code but in actually different. Yeah, so we talked about this, right? It's the same thing. The programming model uses a hierarchy of thread groups. The programming model uses a hierarchy of thread groups. Let me see how much is this. Okay, so they talk about this architecture. Okay. Nice. I'm just looking at the size of the chapter, right? So to see how much of that we can cover today. So it's 45. Okay. So let's go back. It was 4-5, I guess. Okay. Here, right? Let's go. So yeah, it's like 40 pages more. So the program model is a hierarchy of threads. Grid block. So yeah, just guys remember this. Grid block thread. GBT. You have grid. Grid has multiple blocks. Those blocks have multiple threads. So this is the hierarchy. Okay. And it's still like, yeah, this is it's still the same. So then yeah, please keep that in your mind. So these things will come again. Will keep on coming, again and again. So yeah, just keep that in mind. The programming model uses a hierarchy of thread groups. Grid is block and then a thread. Okay, a grid is a set of thread blocks that executes a kernel function. And each block is composed of hundreds of threads. There are 3 memory spaces: local, shared, and global. Local memory space is within a thread, shared memory space is within a block, and global memory is within a... Oh gosh, yeah, this is also really important. So there will be... So we'll see different types of caches as well. I don't know if they have covered here as well. L1 cache, L2 cache, shared memory, streaming multiprocessors. So they will use these concepts. So let's highlight that, and let's also... Let me change this because this is really important. Let me make it red. Orange. I think this is orange. So this is really important, so let's change that. So again, the programming model uses a hierarchy of thread groups. Okay, this is really important. Grid, you have grid has multiple blocks. All those blocks have hundreds of threads. Grid block thread, remember that. Now there are 3 spaces as well. Local. Okay, let me highlight this as well. Okay, this one, can I increase it? No, this is not... Okay, let me just highlight it again. So there are 3 memory spaces: local, shared, and global. Okay, inside the GPU there are 3 memory spaces: local, shared, and global. I'm repeating this because it's really important, and this will come up multiple times as we go ahead. Local memory space is the lowest one, that is shared within a thread, right? Now let's say a thread is being executed. A thread executes a kernel code inside a block. That thread will have access to some memory that is reserved for that thread itself. That's called local memory. Shared memory is shared, as the name itself says. Shared memory space is within a block. Now, as I said, a block can have hundreds of threads. All those threads are executing the same piece of code, same kernel code, but multiple locations, multiple data. Right? We talked about the model, right? SIMD or SPMD. A single instruction or single program, multiple data, right? So then these threads will have a shared memory that they will access, right? So shared memory is shared between the threads in a given block. Now global memory space is within the grid. We talked about it, right? Grid, block, thread. Thread memory is local, block memory is shared memory, grid memory is the grid memory is the global memory. Okay, so Yeah, let's keep that in mind. Maybe we'll keep on revising that. Now, hence threads. Okay, I think I got a message. Okay, got feedback. Gotham says, nice stream. Switch the category to software and game development. Okay, how do you do that? Okay, let me see. I don't know how to do that. How do you change the category? Let's. I have no idea how to change the category, guys. Like, let's see. Change Twitch stream category mid stream. Let's see. Okay. Reddit is the best source of an. If you have any question, just come to Reddit. Okay, it's 7 years old. I don't think it's relevant. Okay, let's see this.
Automatically to take you to your stream manager. If it doesn't, just go ahead and click that. And we're gonna go over now to the edit stream info. Go ahead and click that. And as you can see, we have the title here. Go live note.
Where did he go? He went to stream manager. Do I have that here? Okay. So from Streamlabs, okay, let me see it from Streamlabs. How do I change it? Dashboard. Yes, let's continue. So let's close this. Thanks for the suggestion. But yeah, let me. Let's continue. So let me go there. Okay, the mic is there. Okay. Threads within a block can share data using shared memory. As we saw, threads within a block can share data using shared memory, but across blocks the data must be written back to the global memory, right? So if let's say there are multiple blocks, two blocks want to share something, some data, right? That cannot be kept in the local memory or the shared memory. You have to move that to the global memory, because grid level grid only has access to global memory, right? Thread has access to local memory, the blocks have access to the shared memory, the grid has access to the global memory, right? So if you have to make sure that certain blocks are sharing some memory, you have to move that to the global level, because grid has multiple blocks, a block has multiple threads, right? So I'm just repeating this because this is important. All threads within a block run concurrently using fine-grained multi-threading. All threads within a block run concurrently using fine-grained multi-threading, right? So as I talked to you about, right, SIMD model, all threads within a block, they execute all at once together in groups of warps. Warps are nothing but groups of threads, right? We talked about that as well. A barrier can be enforced within a block. However, I think this is I think what they mean by here. I don't know about like if that's the exact thing, but what I've seen is, let's say there are certain times where you want to do some matrix multiplication, right? Then there is a certain dimension of the matrix. Now you have, let's say, 32. A warp has 32 threads. Now the threads that you need for multiplication are only 16 because the matrix is smaller. Then what do you do with the other 16 that is left? Because as I said, a warp executes all the threads at once, right? So then you have to somehow block the other 16 threads that are executing together with this, right? So then you do some kind of memory, blockage. We'll see how that's done. Even I will learn that. But then I think that is what they mean by here. But then let's read ahead and see. However, depending on the machine resources, blocks are not guaranteed to run concurrently. I mean, obviously, depending on the memory, the RAM that we talked about, right? The VRAM of the GPU, the DRAM that is in the CPU itself. So CUDA also provides two read-only memory spaces, constant space and texture space. So let's highlight this. We will also see because this, as I said, this is from 2012 and CUDA came out in 2007, like 2007 or 8, right? So I mean, let me also verify that, because I've seen that in one of the videos, like in one of the lectures that I was watching. So they said it was 2007. So let me verify that. CUDA come out. So CUDA stands for Compute Unified Device Architecture. Is a parallel computing platform and application programming interface, API, right? Model created by NVIDIA. As I said, right, CUDA was first released in 2007. So I was You were correct. So since then it has gone through numerous updates and versions. Okay, let's ask this as well. Like, is this still the same, the terms that are used here, or the architecture has changed? So let's search that. So yeah, I'm searching it on GPT-4. So I'm using Po from Quora, so it gives you access to multiple models all at once. So usually for these kind of things, I use GPT-4 for writing, and if I have some links that I want to fetch data from, I use Claude. So yeah, right now I'm using GPT-4. So this statement is from, yeah. So my prompt is, this statement is from 2012. I just pasted this, and then I just ask it like, is it still true in 2000? Is it still true in 2024? So its knowledge cutoff is till April 2023. So it will give the results till then, but I think, yeah, like it will be same, right? It is this okay? Let's ask this. CUDA provide multiple CUDA provided multiple memory spaces, including read-only memory spaces such as constant memory and texture memory. Okay, so it does. It's still there. Let's see what it actually is, right? So I will read verbatim from the answer that I got from GPT-4. So constant memory, this is a small read-only cache. Okay, constant memory, this is a small read-only cache that is meant for variables that will not change over the course of a kernel execution and that are shared across all threads. Okay, let me read this again. Constant memory, the name itself has constant, right? This is a small read-only cache. Cache is for faster access, right? Small read-only cache that is meant for variables, right? That will not change over the course of a kernel execution, that are shared across all the threads. Now, a memory that is shared across all the threads, what's that called? We saw about this, right? So it's called local memory. So here, it's constant memory is a read-only cache, read-only memory that is meant for variables that don't change. So you don't because the variables are not changing, you don't have to make it right. Right, I mean, you don't need write access to that, right? Because it's not changing. Just do it once, you don't have to change it. So read-only cache that is meant for variables that will not change over the course of a kernel execution and that are shared across all the threads. This is beneficial when all threads read the same value or values because it's broadcast efficient to all threads. Yeah, okay, makes sense. So constant memory is part of local memory. We talked about that. Now, texture memory. Texture memory is a read-only cache designed for texturing operations in graphic rendering. Okay, what is texture memory? This is a read-only cache designed for texturing operations in graphic rendering. Texture. This is a read-only cache. This is our, so initially, like, constant memory was also a read-only cache. It was small. Texture memory is also a read-only cache designed for texturing operations in graphic rendering, but it can also be used for certain types of read operations. In general, CUDA texture memory has specific caching and memory patterns that can be sometimes of higher performance. Okay, I didn't get this. Like, let's ask. Like, texture was not that clear. So I'm asking it more details about the texture memory because that was not clear. Constant memory, got it. It's a small cache that is meant for variables that don't change over execution of a kernel and are shared between threads. That's clear. Constant memory. Texture memory, I didn't get it. So let me ask it more. Like, question was not clear. How is it different from constant memory? Okay. Texture memory and constant memory in CUDA serve different purpose and are optimized for different access patterns. Okay. Let's see. Constant memory purpose is variables that we talked about this. Same value. Okay, got it. Small. Constant memory is small. We talked about it, but it's in order of kilobytes, KBs, right? It's cache. Values in constant memory is cache. The cache is optimized so that when one thread in a warp reads from its single read, so the cache is optimized so that when one thread in a warp reads from constant memory, it results in a single read, and subsequent reads of the same address by other threads are very fast. So yeah, I don't know if that counts as a read as well. So it says that when a thread from a warp reads from that memory, right, that counts as a single read. Now, as we talked about this, a warp can have multiple threads, right? When other threads after this, right, after the first thread has read from the memory, when other threads come and read, those reads are subsequently faster, right? So I mean, it makes sense because the first time when you're reading, I don't know how the write worked. Like it's already written, right? Because it's a read-only memory. So the data already exists there. It has been written there. The thread goes, reads the data, comes back. It takes some time. Now, when other threads from the same warp go, it takes lesser time than what it took for the first thread. So, interesting. I don't know how it's achieved. Okay, I don't know how this went there. Okay, my screen share stopped. I don't know if there is a way to. So I'm using my tab. Okay, we control K. Control K. Okay, yeah, Windows key is something. All right. Let's go. Why is there a yellow line? Twitch. Okay, let's read this again, and after that we'll go back and again see what texture and constant memory is, right? So threads within a block can share data using shared memory. Okay, we know that. But across blocks, the data must be returned back to the global memory. That's clear as well, right? All threads within a block run concurrently using fine-grained multi-threading. We know that. A barrier can be enforced within a block. We talked about that as well. However, depending on the machine resources, blocks are not guaranteed to run concurrently. It obviously depends on the hardware specification, RAM, the size, and everything, right? CUDA also provides two read-only memory spaces. CUDA also provides two read-only memory spaces, constant space and texture space, right? We saw about constant space. It's a small memory that is shared inside a block by multiple threads, right? So then what is it called? Local shared memory, right? So constant space is a shared memory. It's a cache. It's a small cache, and it's in terms of kilobytes. So yeah, texture space. Let's see about that as well. Because of the broadcast capability, constant memory is most efficient when threads of a warp. So basically, constant space is accessed by groups of threads that are in a warp, right? So it is best used when all threads reach the same value. Okay. Constant memory or constant space is for warp level. Okay. So constant memory is most efficient when all threads of a warp access the same memory location. Constant memory is most efficient when all threads of a warp access the same memory location. Okay, we talk about. Now let's see texture memory, because it was not clear to me earlier. So let's have a shot at it again. Let's see what it really means. Purpose. Texture memory is originally designed for graphics textures, but in CUDA, it is used for data that can benefit from spatial locality. Designed for graphic textures, but in CUDA it is used for data that can benefit from spatial locality. When threads access data locations that are spatially close to another, texture memory may provide better performance. Okay. Texture memory is originally designed for graphics textures. I don't know what that is. Graphics textures, like texture. What does this mean? Like, what does texture means in this context? I don't know. But let's read ahead. But in CUDA, it is used for data that can benefit from spatial locality. I'll read this sentence again. Texture memory is originally designed for graphic textures, but in CUDA, it is used for data that can benefit from spatial locality. Okay, so let's say in the memory space you want certain, like, some data to be near to each other, right? The location of that data, well, like there are certain elements of data that you want to be nearer for accesses, right? So then texture memory is used in that scenario when threads access data location that is spatially as in like on the hardware, like let's say there are two indexes, there are three indexes, 0, 1 and 5, and they are sequentially on a hardware, right? Now 0 and 1 are spatially closer than 0 and 5 in terms of memory locations on the hardware. So I think that is what it means. I mean, I assume when threads access data location that is spatially close to one another, texture memory may provide better performance. Okay, just remember this. Textured memory is when you want spatially close, like data to be spatially closer. That's, remember that. It will be more clear if it's used ahead. It should be more clear, but right now just keep that in mind. Textured memory spatial size. Texture memory can be larger than constant memory, allowing for the storage of more extensive data sets. Okay, larger than constant memory. Cache and access pattern. Texture memory is cached and optimized for 2D spatial locality. 2D spatial locality, meaning that if threads access data that is close together in a 2D layout, meaning that if threads access data that is close together in a 2D layout, think of a matrix on a matrix in memory location. Think about it, because it's a 2D structure, right? Texture memory is cached and optimized for 2D spatial locality, meaning that if threads access data that is close together in a 2D layout, the texture cache can provide accelerated memory access. Okay, maybe let's say your CUDA kernel is doing matrix multiplication. Now all the elements of, let's say it's a 16 cross 16, 4 cross 4 matrix. Now there are 16 elements, right? So then you want those 16 elements to be spatially closer in a 2D unit, right? In that case, maybe texture memory is more useful. So I mean, from at least from the reading this, it seems that way. Hardware interpolation and addressing. Texture memory also provides hardware support for interpolation and various addressing modes like wrapping and clamping, which are useful for graphic operation. Okay, I think this is overkill for us. So we got a general idea, right? As we go ahead, if this is being used more frequently, we should get a better idea, and then maybe we can come back to this again. Let's go. CUDA provides two read-only memory spaces, constant memory space and texture memory space, right? For now, remember that. Mapping the programming model to architecture. Figure 1. So where's the figure 1? Okay, this is the figure 1 for the GPU architecture. Figure 1 shows the high-level view of GPU architecture. The version for GPU in the figure is NVIDIA's G80 architecture, which is applicable to these series of GPUs that we actually use. So, okay. I think still, basic architecture would, I guess, it's still the same, right? Just the quantity would have increased. It would have been scaled depending on the computation load that we have today. But then still the base architecture would be similar. So I think, yeah, even though I don't think we use these GPUs anymore, but still, the architecture can help us get an idea of what an architecture of current GPUs in today's world looks like. So yeah, let's go through this. The version mapping. Okay, let me see this. Okay. Just give me a second. There has to be. So let's go. Talks about the old, the architecture, it talks about the type of GPU. Changes 4, 5, 11. Okay, the architecture consists of a scalable number of streaming multiprocessors. each streaming multiprocessor contains 8 streaming processors. Streaming multiprocessor contains streaming processor, as the name says. 2 special function units, SFU. I think these terms will keep on coming, so keep those in mind. Special function units. I think some of the special function units are optimized for mathematical operations, so that's their job. How do you let's say for example, how do you efficiently execute matrix multiplication, right? Just to give an example. So then that's SFU. So let me highlight this. A multi-threaded instruction fetch unit. A multi-threaded instruction fetch unit. A read-only constant cache. 16 GB shared memory. ठीक है ना? So just a second. 77. Okay. Each streaming multiplayer contains 8 streaming processors, 2 special. Okay. Yeah, I don't think. Yeah, that's too. We can skip that. Threads are dispatched to SMS. Okay. So threads are dispatched to SM. SM is streaming multiprocessor. Each streaming multiprocessor contains 8 streaming processors. So let me also highlight this. I'll make it yellow this time, so it's. So terms and all, the terms or certain statements, definitions, I'll highlight in orange. Important points I'll highlight in yellow, and then we'll see what more colors we need as we go. A multi-threaded instruction fetch or read-only. Okay, threads are dispatched to streaming block granularity. So in a block there are multiple threads. Now streaming multiprocessor will be assigned threads, but in groups of blocks, right? So the number of blocks that can be assigned to a streaming multiprocessor depends on the available resources, which is obvious, right? I mean, as we saw, right, all the threads, they need certain amount of memory. There is a threshold, right, a bottleneck. So depending on that as well, how many threads or how many warps, how many blocks you can execute on a given streaming multiprocessor, it's limited, right? You can do limited number of blocks for a given SM. So the number of blocks that can be assigned to SM depends on the availability of resource. Yes. Yeah, as we talked, right, the amount of resources each block uses. Now if the maximum number of threads is assigned to SM, the occupancy matrix, so basically each SM has some threshold, right? It has some bandwidth. You use that whole bandwidth is what it means here. Maximum number of thread is assigned to an SM. The occupancy metric is 1. So it makes sense, right? Number of threads that is being used by the streaming multiprocessor upon the max number of threads that can be used by the streaming multiprocessor, right? Now let's say if you make the numerator as max number of threads, it will become 1, right? So then the occupancy matrix, how much of the streaming multiprocessor is occupied, is 1, because you are assigning maximum number of threads that it can possess, handle. During execution, SM forms a batch of 32 threads together, okay, called a warp. Yeah, so warp is group of 32 threads. I think I've talked about this, the number 32. During execution, SM, streaming multiplier, forms a batch of 32 threads together called a warp, which is the granularity of single instruction multiple data execution. This is very important. Let me highlight this in. Let me change the color to something important, like green. Green looks nice. Okay, so during execution, SM forms a batch of 32 threads called a warp. Just a second, give me 1 second, okay? During execution, streaming multiprocessor forms a batch of 32 threads together. During execution, SM forms a batch of 32 threads together called a warp, which is the granularity of single instruction multiple data execution. Now, let's zoom this a bit and let's look at the image. So that should clear like a lot of things. So, okay, let's read this sentence again and then come zoom it back. During execution, SM forms a batch of 32 threads called warp. Group of threads is warp. That number of elements in that group is 32. 32 threads form a warp. Remember that. Who forms that threads? Like who forms that group? The streaming multiprocessor does it. Okay. During execution, SM forms a batch of 32 threads together called a warp, which is the granularity of a single instruction multiple data execution. So we talked about this, right? Single instruction, that is single kernel code or whatever instruction, is being executed by the threads but on multiple data locations. That is SIMD model, right? And we talked about SPMD model as well in the beginning. So a single instruction is executed by 32 threads. That's like the granularity, at least 32 threads. So now let's zoom on this image. I hope it's visible. Let me zoom this some more. Okay. So warp. Look at this, right? We saw about this. Thread forms a warp. Number of threads is 32, right? Now, you have multiple warps like this. All these warps are inside a block, right? So, block is, which we said, right? Block is a group of threads. Block has multiple threads. Now, all those threads, you break it down into, like, you bunch them into 32, right? Group of 32 threads each. Those are called warps. So we talked about the hierarchy, right? That hierarchy still remains same. It's just that between block and threads you have warps. Warps are groups of threads. Remember that. Now, inside block you had multiple threads. You group them into warps. So you have multiple warps inside the block. Got it? Now, similarly you have multiple blocks now. Okay. These blocks form, like all these blocks are part of a single streaming SM. So basically, and each SM has multiple processors, like streaming processors. So I think it has 8, if I'm not wrong. It says 8, right? Number of blocks, okay. Yeah, so I think, yeah, this is for this GPU. I don't know, maybe the newer generation has more or less. The number is different, but then for this one, SM has 8 SPs. So streaming multiprocessor did the grouping of WOPs. All those WOPs form a part, like all those WOPs have certain threads. Those threads are part of a block. Now one streaming multiprocessor can have multiple blocks. So now what's that number of how the number of blocks changes, and then what can be the max number, and all those things we'll have to read more. So maybe we'll figure out as we read. But then, yeah, you see this single SM has, let's say for here it's two blocks. Now all these streaming multiprocessors, so a given GPU will have, I think when you buy a GPU, on the box itself, then like it will tell that this is the number of SM or number of streaming multipliers that this GPU has. Like from, I think that is the case from what I know. So yeah, now let's see like what is the internals of this streaming multiprocessor. So it has cache, decoder, shared memory, streaming multiprocessor. So we talked about this, right? 8 of these for this generation of GPU. So one SM has multiple SPs, and this is the SIMD execution module. So this group of SPs is the SIMD execution module. Single instruction, multiple data. Shared memory, decoder, cache, PC. We'll see now more of these. All of these SMs form a network. Then network is the global memory, the device memory. So when like in like CUDA programming and then like computing, parallel computing, the two terms, device and host. When you hear device, it means the GPU. When you hear the host, it means the CPU. Like remember that, right? So here global memory is the device memory, the GPU memory. Okay, so let's zoom out, read ahead and see more. I think, yeah, they must have given more information about this architecture of the SM itself. So the cache, the decoder, shared memory. So we'll see more. I hope so. Okay. So executing a warp instruction applies the same instruction to 32 threads. Yeah, we know that. Similar to executing a similar to executing a streaming SIMD extension instruction is at 86 architecture. The concept of warp is not exposed to the programmers, so they do not have explicit on the hardware. Okay. From the warp for execution. Okay, so the warp creation and all, we talked about that. Like the streaming multiprocessor takes care of that. The developer has no control over it. The blocks that are running on SM are called active blocks. Okay, let me highlight this. So in this example, we saw that for one SM there are 2 blocks. So I think, yeah, those 2 blocks will be called active blocks that are running at like in one instance. Okay. Since one block typically has several warps, which is the number of threads in a block, divided by 32, the number of active warps per SM is equal to the number of warps per block multiplied by. Okay, let's read this slowly. One block has several warps, right? Let's say one block has multiple threads. One warp has 32 threads. So then for a block, the number of warps equals to the block size, that is the total number of threads, divided by. So the block has multiple threads, right? So let's say 64 threads. Now WOP is a group of 32 threads, right? So then for a given block, the number of WOPs equals to the total number of threads in that block divided by 32. So 64 by 32 is 2. So then a given block, like that given block that we have in the example, has 2 WOPs, right? So then, as it says, the total number of active WOPs per SM per streaming multiprocessor is equal to the number of WOPs per block multiplied by number of active blocks. Okay, since it's now I don't know, like, do they assume that all the like for a given SM, let's say it has 2 blocks, those blocks has multiple threads, they're grouped into WOP, like all of those are active? So that's my doubt. I mean, yeah, since one block has several WOPs, number of threads in a block 32, yeah, that makes sense. The total number of active WOPs per SM is equal to the total number of active WOPs per SM per streaming mode is equal to number of WOPs per block. We talked about that, multiplied by the number of active blocks. Block. Okay, yeah, makes sense. So let's say you have one block has 2 WOPs and one SM has 2 blocks. So then you have 4 WOPs, right? Basically, WOP per block, that is 2, into blocks per SM, that is 2. 2 to the 4. So 4 WOPs per that SM. So, and yeah, the active WOPs basically. So yeah, this is important, and there'll be more terms as we keep on reading, right? WOPs, block, grid, local memory, shared memory, global memory, caches. So just keep on dumping those things, and then we'll keep on repeating them again and again. So yeah, that should be clear. But yeah, and then all these things are, like, as I said, this is from 2012. This thesis, CUDA came out in 2008. Right now it's 2023, 2024, right? But still, like, all those things, like, from what I've seen, like, these things are still the same. Like, the basic is same, right? It has been scaled to have, like, cover more compute, but then the basics are still same. The memory architecture is still same, right? It has been scaled, as I said, but then yeah, the basics are still same. So if you learn this, that should be clear. So there's a book called PMPP, so Programming Massively Parallel Processors. So it's like one of the most famous books. So anyone who is in CUDA, like, they'll suggest you to read that. So initial chapters of that book, like, this is exactly what it covers there. So I've read some of it, not completely, but yeah, I think after we read this chapter, especially the second chapter, a lot of those things should be clear. So yeah, let's continue. The shared memory is implemented as a static random access memory. The shared memory. So again, let's revise. Thread has access to some memory that is only accessible to that thread itself. That's called local memory, right? Now, a block has multiple threads. All those threads share some memory amongst themselves. That's called shared memory. Now, a grid has multiple blocks. Those blocks share some memory amongst themselves as well. That's called global memory, right? I'm just revising things. So now let's read this again. The shared memory is implemented as a static random access memory. Whereas, so this is a shared memory, right? And shared memory is the one that is shared between the threads. Let's highlight this. In a block, it's static RAM. Whereas global memory, that is between the blocks. This is between the threads, this is between the blocks. Okay. Dynamic RAM. So I mean, I have to, let's see if they have, like, what do they mean, because yeah, like I'll have to go back and brush up my concepts on what static and dynamic in terms of RAM is, the internal architecture. So maybe we can ask GPT-4 to revise that. So I think we have done all of these in our undergrad, but yeah, let's also, this footnote is for the metric, the occupancy metric, I think so. But yeah, I think we've gone through that. But uh, uh, let's read that. The metric is the ratio of assigned threads to maximum. Yeah, I mean it makes sense. So basically, if you, it said that the metric is 1 when you assign the maximum number of threads that a SM can take, right? And it makes sense. Like if you SM has, let's say, 2 blocks, those blocks has multiple warps. You, the code that you have written uses all the threads, right? And then it has some maximum threshold, like SM can have certain memory, certain, like it has 8 streaming processors and all of that, right? So it has some threshold, like bandwidth, the max bandwidth, right? If you occupy all of those threads, then it will be 1, like the ratio will be 1. So it makes sense. Total number of threads upon max number of threads. Now if the total equals to max, it's 1. As simple as that. Higher occupancy means more threads per SM. The ratio, the max is 1. Hence, idle memory cycles are hidden more effectively with more. Okay, this is interesting. Let's read this again. The metric is the ratio of assigned threads to maximum threads. That's clear. Higher occupancy means more threads per SM. That's clear as well. Now, hence, idle memory cycles. Idle memory cycles are hidden more effectively with more available threads. Okay, idle memory. Just trying to understand this. Idle memory cycles are hidden more effectively. Idle memory cycles. Okay, let's ask GPT-4 this. What is this? Because yeah, I'm trying to know what's idle memory cycles. Memory cycle is when you go and fetch something from the memory. That's the memory access, right? Now, what is idle? Because if there is a memory access, then it's not. I mean, like the term idle doesn't make sense in that context, right? But then if it's idle, then no access has been made. Then how is that a cycle? Like if so, let's ask. Let me put the whole thing. Okay, where was this footnote again? Let me zoom out a bit because we've already gone through the diagram. So, okay. 2, right? Occupancy matrix. Okay. V. So I'm just asking this, like, to explain this paragraph, like this thing, this last line to GPT-4, just what this thing means, right? So let's see what. Okay, let's do this. Okay. Let explain the idle memory life cycle in the below given. So let's see what's the next checkpoint. So maybe we'll cover this today. After this, yeah, okay. I think we will stop at 2.1. 2.1 was the background, right? So yeah, after this we'll have like a good understanding of the architecture, like the terms and everything, right? So that should help us understand the next part. So for today we will go through this, like the section 2.1 as well itself. Then tomorrow, maybe in the next stream, we will cover this, like the program analysis part, like their work, what they did, right? What the author did. We'll cover that tomorrow. So today we'll form a base on how the architecture works. So we have 2 more pages. Okay, so I asked GPT-4 about this definition and what idle memory cycle means here, and I will read the answer now, and we'll see what that actually is, right? So in CUDA, the concept of occupancy relates to how much of the GPU's resources are being utilized by the threads, right? So yeah, I mean, you must have heard about the term GPU utilization. So I think, yeah, this is what this kind of means as well, the number of threads that are being executed and what's the total threshold, like maximum capacity of that streaming multiprocessor, right? So specifically, it is measure of how many threads are active or can be active on an SM related to the total number of threads that the SM can handle. Okay, SM is the fundamental unit of computation on NVIDIA GPU. Each SM can execute a certain number of threads concurrently. Okay. Maximum number of threads per SM. Highest number of threads that can be theoretically assigned to an SM. It's determined by the hardware capability of SM. Okay. Now, occupancy metric. I think we already talked about this, but let's go through that again as well. The occupancy metric is calculated as the ratio of the number of threads that are currently assigned to a streaming multiprocessor to the maximum number of threads that can be assigned to a streaming multi, like theoretical limit upon the actual limit, like upon the actual number of threads. So that's the occupancy metric. If you exhaust the complete capacity of a streaming multiprocessor, you will reach like one occupancy metric, right? We saw that in the example in the text. Now, yeah, it says that as well, like the GPT-4 response says that as well. An occupancy of 1 means that SM is fully utilized in terms of thread allocation. So you are basically like getting full use out of it. No more threads can be assigned to it. Okay. Now, this is what a doubt was, right? From that definition, idle memory life cycle. So let's go through this and let's understand what it means. So these are cycles during which the memory subsystem can be, the caches, registers, global memory, all of those things, right? I'll read this again. These are cycles during which the memory subsystem is not being used. Okay. So this is like the hardware cycle. Okay, now it makes sense. This can occur when threads are not active or are waiting for some operation to complete, such as memory fetcher. Okay. Maybe we'll take some example of this as well. But now it's clear, like when during which memory subsystem is not being used. Okay, the threads are not active. Okay, let's say when a thread is not active. I mean, a hardware already has its frequency and cycles, right? Now, there are certain cycles where memory is not being used for whatever reason, right? Maybe the threads are busy somewhere, or there is some other reason that the memory is not being used, like the cache, the registers, the global memory, local memory, shared memory. Nothing is being used. There is no read access or there is no memory access being performed. That that period, those cycles are called idle memory cycles, and the name, I mean, it makes sense as well. So now, I mean, I was confusing this with like a different cycle, like the memory cycle that we talked about. But this is the memory access that we talked about earlier. But yeah, this is when it's not being used. As simple as that, right? Not to complicate things. When memory is not being used, it's idle. It's called idle memory cycle. Like let's right, as simple as that. This can occur when threads are not active. Makes sense? Or are waiting for some operation to complete, such as memory fetch or arithmetic operation. Here it's a bit ambiguous. It says that the memory subsystem is not being used in the first line. In the next line, it says that the threads are not active or are waiting for some operation to complete. Now that operation, the example they've given is called memory, is one of the operation is memory fetch. But if a thread is idle right now because it's waiting for an operation to complete and that operation is memory fetch, how can you call that, like idle memory cycle? Because the initial base is that memory is inactive at that point because no thread is using that memory. But then still you are saying that the thread is not using that memory because of the thread, like memory fetch. So yeah, that's a bit unclear, but okay, that's okay. Let's maybe we will get some more idea as we read. Hiding idle memory cycles. High occupancy can help hide these idle memory cycles. With more threads available to an SM, the GPU can switch between threads when some are waiting. Okay. This is okay. So you think about this. Let's say you have multiple threads. Let's say you have hundreds of threads that you want to execute right now. From that, like those hundreds of threads, certain subset is waiting for some operation. Then, while those threads are waiting, why don't we use other threads and start executing them in parallel, right? So that latency is reduced. Like it's basically you're hiding that latency, right? Let's say some threads are waiting for some operation. Sequentially, you keep other threads waiting as well, even though they have no dependence on this thread's execution, right? Then you will have some latency. But if you start executing those threads in parallel as well, that latency will be hidden, right, from the users. So I think, yeah, that makes sense. Well, one thread is waiting, another can be executed, this keep busy and keeping, yeah. Also, you are keeping the hardware busy, which is what we want. Okay. So that's called idle memory life cycle. You are hiding that. Memory latency. The delay between a request to access memory and the fulfillment of the request can be performed. Okay. Memory latency. The delay between a request to access memory and the fulfillment of that request can often be a performance bottleneck. So let me see if my voice is okay. Maybe I'll keep this a bit far. Okay, so let me see when's the last bus that I need to catch. Okay, so there is a bus at 12:14, 12:29. The last bus is at 12:29. Okay, so we have maybe an hour. We have 2 pages. So I'll try to complete them. Okay, let's go. Okay. That's nice. Okay, yeah. Warp. Let's read this. The shared memory has very low access latency, which is almost the same as that of accessing a register. So basically, they're saying it's quite fast, right? As fast as a register. Okay. However, when a warp accesses the shared memory simultaneously, causing bank conflicts to occur within a warp, so additional delays occurs. Okay. I mean, yeah, okay. When a warp accesses shared memory simultaneously, okay. shared memory is between blocks. Is shared within a block, like threads within a block, right? Now, let's say there are 2 3 uh, verbs that are trying to access some memory, shared memory within a block, right? That can have some latency, like delay. So this is what they're talking about. Section mapping the programming model to the architecture is complete. Okay, now we will see how the warp execution works and types of memory accesses. Okay, now streaming multiprocessor SM executes one warp as a single instruction multiple thread. We talked about this. Multiple thread. Okay, multiple threads. Okay, this is different. This is what we saw earlier was single instruction multiple data. This is single instruction multiple threads. I mean, yeah, I think it's the same thing at the end, because there as well, like single instruction is the same kernel code, multiple data. So then multiple data is being accessed by multiple threads in itself, right? So then I think the crux is the same. But yeah, let's see, let's read it again. SM executes one warp as, so warp has 32 threads, right? Now you, as we saw, like thread, like warp is the basic unit of computation, right, for a GPU. So when you execute a warp, you execute those 32 threads all together. So then in that case, you are executing one instruction but multiple threads on that same instruction, right? And then those same threads can access like multiple data as well. So you can also call that SIMD model. Like, so yeah, and schedules warps in time sharing fashion. Okay, so one SM can have multiple warps. We saw that. So how are those executed? Like you cannot do all of the warps all at once, right? So there has to be some kind of scheduling, like round robin or a random or any other, right? So then here it says schedules warps in time sharing fashion. So we'll see what the strategy is. The processor has enough functional units and register ports to execute 32 threads together, right? So now this is one warp. Okay, 32 threads is one warp. So the processor, I don't know what, like when they say processor, do they mean SM or SP? Because one SM has multiple SPs, right? So if let's say one SM, in this architecture it has 8 SPs, and each SP has 32 threads, that is one warp, then one SM can execute 8 warps simultaneously, right, concurrently. So let's see if they mean by, I assume they mean SM, but because see, if they mean SM 32 threads, then there are 8 32 by 8 4. Okay, then each SP will have 4 threads. I think that's too less. I don't know. Let's see. The processor has enough functional units and register ports to execute 32 threads. Since SM has 8, oh yeah, see, you see, this is what they talked about, because it makes no sense if one SM has 8 SPs, but still the bandwidth of one whole SM is just 32 threads, because then each SP would have, because there are 8 SPs, 32 by 8 will only have 4 threads, which I think is quite low, to be honest, right? So in this case they are talking about those SPs. So then each SP is 32, so then SM will have 32 into 8. You get it? So yeah, that's a good number. That's a good number. The processor. Nice. This should be interesting. So yeah, let's first highlight this. Functional units and register ports to execute 22 threads together. Since SM has 8 functional units, figure 2 issuing 32 takes 4 processor cycles for computational instruction. Okay, what does this mean? 4. Okay. No. I think our initial assumption was correct. What I saw what I said, right? It would be quite low. I think that's correct, because what it says is, since SM has 8 functional units. Now by functional unit, I think they mean SPs. And when they say processor here, just processor, they mean the SM itself. So 32 threads are 32 threads for the SM itself. That SM has 8 SPs, 8 functional units. Each of the 8 will have 4 threads each, let's say, right? So 8 for the 32. Now those threads, 4 threads, they are done in 4 cycles, I think sequentially. Okay, I don't know. Wait, let's. Four processor cycles for computation. Okay, let's see the footnote. A computation instruction means a non-memory instruction. When a memory instruction is executed, SM generates memory transactions and switches to another warp until all the memory values in the warp are ready. When a memory instruction is executed, excuse memory transaction switches to another warp. Okay, so basically, instead of waiting, it generates the memory transaction and then switches to a different warp, right? Instead of just waiting, so that you sequentially complete. So it's kind of sequential, but then it looks like it's in parallel. When a memory instruction is executed, okay. When a memory instruction is executed, SM generates memory transactions and switches to another warp until all memory values. Okay. Ideally, all memory requests within the warp can be combined into one or more memory transactions. Unfortunately, that depends on the access patterns within warp, the first memory address, the requested data size, and the hardware. Okay, they are saying that all the memory requests within the warp, so that is all the memory requests of all the threads within the warp can be done in just one transaction, but that depends on the type of data, the address of the data, and then data size. So yeah, different factors, right? So GPU, for the list of GPU products with different compute versions, the CUDA manual should be referenced for the different. Okay, warp execution. I think I still have like one or two things unclear here, I think, but let's ask GPT-4. Sorry. Okay. Figure 2. Let's see this figure. Let me increase. Okay, so we're done with 2 hours of streaming. That's good. I'll try to keep up with that. Maybe an hour or two every day. Maybe during this time, we'll learn something. Maybe we'll go through some papers, some thesis, maybe some coding as well if I'm feeling good. But yeah, we'll try to learn something new during this time every day. Yep. Ideally, all memory requests within warp can be combined into one. Okay, I think I got a response from GPT-4, so let's go through that. CUDA. In CUDA, streaming multiprocessor executes instructions using a model called SIMT, single instruction multiple threads. A warp is the basic unit of thread execution in CUDA. Remember that. Basic unit of thread execution. Okay. And typically consider 32 threads that execute the same instruction at a time. Okay, we know that. Warp execution. Okay, the SM executes one warp at a time using the SIMT model. Okay, the SM executes one warp at a time. One warp at a time. Meaning, all threads in the warp execute the same instruction concurrently. If the instruction is computation, like addition or multiplication, all threads perform this operation on their own set of data. We know that. So then this is what SIMD is, right? Here there are SIMT, but then if the instruction is a computation, all threads perform this operation on their own set of data. Instruction is same, data is different. SIMD. Okay, so okay, just a second. So, time sharing fashion. The SM schedules multiple warps. I think there should be a way to paste it, like quickly paste the answers and. Okay, let me. Should I open? Okay, let me do this. Let me open this. Let me open a notepad. So that it's easier for all of you. So I'll generate, like, if you have questions, I'll generate some answers from GPT-4, and then I'll paste it on this notepad, and then we can go through that answer instead of me just reading and you not seeing the text. I would say like it would be better, right, if all of you see the text as well. So let me open a new text file. Okay, let me delete this. So let me copy, paste. Oh, sorry, didn't copy. Copy, paste. What? Why is it not copying? No, not selected. Copy message, yeah. Paste. Do you think a Word document would be better? I don't know. Okay, give me a second. I'll be back. Oh, sorry. Yep, so let's go back to where we stopped. When a memory instruction is executed, SM generates memory transactions and switches to another warp until all the memory values in the warp are ready. Okay, so uh, as we said, right, some warps can share some memory location. So we don't want those warps to like wait, like the other warps to wait till one warp execution completes, right? So what it does, it SM starts a memory transaction, then start executing other warps that may not be using that. Instead of waiting, we just start with the other warps, right? So it's kind of parallelization, so that hides the latency of the execution of warps. So ideally all memory requests within the warp can be combined into one or more memory transaction. We talked about this as well. Unfortunately, that depends on the memory access pattern, the first memory address, and things like that. So how much memory is there in those requests, the address of the data that needs to be accessed, all of those things, right? So ideally an SM can execute where did it go? Yeah, within the warp. So one SM can ideally execute 32 threads all at once in one transaction, like memory request of all the threads in one transaction. But then depending on how much memory is needed, what's the address of that memory, all those things that are being talked here, that may not always be possible, but in ideal scenario it's possible. So this is the warp execution diagram. So let's see each one of them. Let's see each component one by one. So you have multiple instructions. The model is SIMT, single instruction multiple threads, right? So right now instruction 1 is being executed, single instruction multiple threads by all of these threads. One thread, one warp has 32 threads. Okay, so this one, this warp right now, let's say is executing instruction 1. So that has SIMD execution unit. SIMD is single instruction multiple data. Now all these threads, even though are executing the same instruction or same kernel code, they are accessing different data, right? So let's say if you're doing multiple, like if you're doing addition of let's say 10 numbers, right, 10 digits, all these threads will have one pair of digits each. The operation is addition at the end, right? So the instruction is same, but then the data that is being added is different, right? So that is the same thing here. SIMD, single instruction multiple data execution unit. And this is SP. SP is streaming processor. So one streaming multiprocessor has multiple streaming processors. In this architecture, the architecture that they are talking about from 2012, one SM has 12 SPs. Now I don't know about like the latest generation, like how many SPs are there in one SM, but then the one that they are taking, it has 8. So as you see, there are 8 SPs, right? So now from this statement that we talked about here, if an SM is executing 32 threads and each one of the SM has 8 SPs, then per SP there will be 4 threads, right? So then 4 cycles. That is what is being talked here. So these 32 threads go to this SIMD unit and then equally distributed between each of these SPs. So 4 each. Okay. To illustrate the high level view of a memory transaction, figure 3 illustrates 3 cases. Also, yeah, let's go back to the GPT-4 response as well. So I tried pasting it on VS Code. Maybe later on we can paste on Word doc. But yeah, for now let's just go through. I'll go through and I'll just read. Okay. In CUDA, an SM executes instruction using a model called SIMT. A warp is the basic unit of thread execution. Okay, that's true. The SM executes one warp at a time. One warp at a time. 32 threads at a time. Remember that. Meaning all threads in a warp execute the same instruction concurrently. If the instruction is a computation, all threads perform this operation on their own set of data. SIMD. Time sharing fashion. The SM schedules multiple warps and switches between them in a time sharing manner. So, in one instance, one SM will execute one warp, but then when it executes one warp, it won't keep other warps waiting, right? Because this warp that is being executed needs some memory and there is some latency, right? Like memory access, all of that thing. So it starts the transaction, then while that's happening, it starts executing other warps as well, right? So even though at one instance it can only execute one warp, but then it won't wait for its execution to complete. It will start concurrently execution of other warps. Okay. The SM can execute instructions from another warp, thus hiding the memory latency and keeping the functional unit busy, right? Because you don't want the memory unit, because there is a memory transaction, there is a latency, you don't want the memory unit to, just because the memory unit is busy, you don't want the computation unit to be free. That's why when a warp is trying to access some memory and there is a latency in the memory unit, you start computation for other warps. That's what they're trying to say. Function units and register ports. The GPU has a certain number of functional units that can execute operations. Enough register ports to execute the execution of 32 threads simultaneously. Okay. 4-cycle logic. That is being talked here. This one, right? This was something that was unclear, so we will read that. If the SM has 8 functional unit, it can execute operation from 8 threads in one life cycle. Okay. So just a second. If the SM has 8 functional units, it can execute operations from 8 threads in one cycle. To execute the same operation for alternative threads in a warp, the SM would need 4 cycles. Okay. Let me slowly read this again. Okay, because it can be a bit confusing. And after this we have one more page and then we are done. So because I have a bus to catch, so the last bus is at, right now it's 11:47 here and the last bus is at 12:26 a.m. so I have to catch that or I will have to walk home. So let's wrap it before that. Ideally, all memory requests within the warp can be combined into one or more memory transactions. Oh, sorry, I was reading the wrong thing. So let's talk about the 4-cycle logic, right? Like this statement. Since SM has 8 functional units, as shown in figure 2, issuing 32 threads. This is 32 threads. Takes 4 processor cycles for computation instructions. Let me try to understand that. So Okay. Okay, so you see each processor, each streaming processor can execute one instruction in one life cycle, in one cycle. Okay, now one streaming multiprocessor has 32 threads. Okay, basically 32 instructions are being executed, same instruction but 32 times. Right now, because an SM has 8 functional units that are streaming processors, each of them will in one cycle will pick up one thread, execute them. So then, because there are 32 instructions, 32 threads, 8 functional units that are streaming processor, it will, let's say in one cycle you pick 8 out of these 32, 8, then again 8, then again 8, and then again 8. So you have to do it 4 times. So that's why it says 4 life cycles. So now it's clear. Okay, so in one cycle you can execute one thread. So let's say there are 8 units in one cycle, each one of them will execute one thread. So then in one cycle you will have 8 of them. So then 8 plus 8 plus 8 plus 8, you will have to, so basically it will reach till 32 threads. So when you are executing one warp per streaming multiprocessor, you will take 4 life cycles, 4 cycles, okay, for execution. So that's why this statement is now a bit clearer, right? And as we talked about that, a streaming processor, when one warp is being executed and it needs some memory, it will keep that warp aside and start other warps execution who need just computation, because we won't let the memory execution block the computation, right? So because we don't want that one warp is just waiting for memory, is not using any computation, then other warps that just need computation, we will start their execution. We don't want them to be waiting, them to wait. So then we can hide the latency of the system in a way, right? Because we are parallelly executing 2 warps, let's say. So then, yeah, that part is clear. Now let's read ahead. So to illustrate the high level view of memory transaction, figure 3 illustrates 3 cases. Regardless of the hardware version, when the first requested address is aligned to 60. Okay, let's see the diagram once so that it's much clearer, the text that we are reading. So figure 3, memory transactions. They say they have shown 3 types of transactions, right? So coalesced, uncoalesced, and optimized, right? So A, B, C. This is A, B, and C. So a single memory transaction, multiple memory transactions in an optimized manner. Okay. So you see the 32 address blocks in the data. Each block is accessed by one thread each. So let's say you have a warp. A warp has 32 threads. That warp is accessing this 32 address blocks, because you have 32 threads, right? One thread per block. So this is called a single memory transaction, because all of them are happening in one go. Okay. Now let's see how multiple memory transaction works. So this is thread 1, address 1, thread 2. Okay. So I think here, because they are spatially together, we talked about this in the textured memory, textured space, right? There are certain cases like textured memory is used when you want your data to be spatially together, right? I think this is what kind of means. I don't know if this is the exact example, but then this is a good image or good example to cover that concept as well. A single memory transaction. So all these data like addresses are, let's say if the index of this address location is some hexadecimal and then let's say 1. This will be 2, 3, 4. All of them are consecutive to each other, right? But here these location of these blocks are not consecutive. They are like on different locations of the spatial, like they're not spatially together, right? In the memory hardware, in the location. So then you will have to like do multiple transactions, like fetch this, then fetch this, fetch this, fetch this. Here you can just fetch all of them together because they're together in the memory, right? I think I mean that is what my understanding is. We'll read that and maybe it would be much clearer if there is any misunderstanding. This is multiple memory transactions optimized. So address 1, address 2, address 3, address 16. Okay, so maybe what they're doing is out of these 32, there can be subset of these groups which are spatially together, right? So maybe they're clubbing them together. So for example, here they saw that out of these 32 transactions that are being done, maybe 1, 2, 3, 16. Just a second, guys. Can I move this to top? No. Okay. So I'm just checking the mic if it's going over. Okay. So address 1, address 3, address 2, address 3, address 16, address 30, and then some more. So all of them were spatially together. So they got that in one transaction, then clubbed others in another transaction. Let's say you have 4 or 5 subsets like that in this 32 threads. So then you will just have to do 4 or 5 transactions instead of doing 32 transactions, right? So yeah, that's the optimized way of doing multiple transactions. So let's go back to the text and read again. It would be much clearer. To illustrate the high-level view of memory transactions, because it is okay, regardless of the transaction hardware version, when the first request address is aligned to 64 bytes, the subsequent address are sequential, then only one memory. Okay, yeah, which is what we talked about, right? All of them are sequential, so then you just need one transaction. When the first requested address, that is the thread one's, in the diagram we saw, right? Thread one's address, and then everything else is after that sequentially. So when the first request address is aligned to 64 bytes, the subsequent address are sequential, and the subsequent addresses are sequential, then only one memory transaction is generated. I'm not sure whether it's 64 bytes. Let's ask about this. I mean, yeah, let's first read all of this. Officially not met, then either case B or C can occur depending on CPU. Earlier version of one input will occur for the earlier versions of 1.1 input where multiple memory transactions are generated. This consumes memory bandwidth and degrades performance, obviously. Because SM is an in-order processor, the warp cannot continue executing until all the memory transactions are serviced. So for a warp, all the threads have to complete, right? So without that, a warp cannot continue execution. Like all the memory transactions are to be completed. So for the versions 1.13, the number of memory transactions is optimized by hardware to reduce them and shown in figure C. Even if the first memory is unaligned, the hardware will attempt to generate 2 large memory transactions for each memory segment rather than generating one transaction for. Even if the memory is unaligned, the hardware will attempt to generate 2 large memory transactions for each memory segment. Getting one transaction for each thread. To facilitate the discussion, a memory request is a coalesced access if only one memory transaction is generated, and an uncoalesced access otherwise. A local memory access is treated as the same as a global memory access. Okay, I mean, yeah, it's clearer. Now it's clear, I guess, right? Local memory, this line is a local memory access is the same as the. So basically, both the local memory access, that is the thread level, and global memory, that is the grid level, all of them execute in a similar fashion, right? So there are 3 ways of doing it. I don't know what the version they're talking about, like what version of what. Anyways, so yeah, I think we are done with this. So we have covered a significant amount of work today. So I think most of our base is clear now about the architecture and how the memory access pattern and everything works, right? From this from this background, we will start reading this and see how it goes. Okay, so yes, for today I think that's it. We'll continue maybe tomorrow or day after. All right, so yeah, thank you so much. This was my first stream and it was fun, to be honest. Yeah, we'll try to improve in the next streams. Okay, thank you. Bye. Good night, good morning, good evening.